introduce you to David Chan. He is one of our consultants at Stat Central, and you've been with us 2 years?
2 years,
Two years, 2 years, yes. He comes to us from New Zealand, and he's got a lot of experience in ecological statistics. But he gave this talk as one of his first talks when he was with us. It was a really nice exploration of ideas about data visualization and the different stories that you can tell. So, David, take it away.
Sweet. Thanks, Nancy, for the introduction. So, you're probably wondering why statisticians care about data visualization. And I think the best quote for this comes from the creator of the box plot, that the greatest value of a picture is when it forces us to notice what we never expected to see. So this is by John Tukey. And pictures are great because the human eye is very good at picking up patterns. So this is probably the most interactive part of the talk, is statistical synonyms for picture. So who may have learned about data visualization and what we describe it as a plot? So scatter plot, box plot, so on. This term is used interchangeably with graph, so bar graphs, pie graphs, so on. And probably if you're a bit older, you may have learned it as a chart. And these are all synonyms, and I'll probably use them interchangeably based off whichever plot I'm talking about. But just know that we're all talking about the same thing. We're talking about a visualization of data. So to build upon why we visualize data in statistics, first thing is, it's a quick and accurate interpretation of data. We're not trying to numerically summarize data into, say, a mean and standard deviation. We want to actually see what's going on underneath the hood of that calculation. And data visualization is a very easy way of seeing what's going on. The second thing, and this is coming more from the artistic side of data visualization, so what you typically see in news articles and whatnot, is that we're visualizing data to tell a story. And this comes from one of the most prominent, this particular idea comes from one of the most prominent data journalists out there in the world, Alberto Cardo. And lastly, and this is more arisen from the kind of modus operandi of people using statistical tests to assess model assumptions, is that actually, because we can utilize the human eye to look for patterns, this has developed a new set of data visualizations to assess the diagnosis of statistical relationships. So those are the 3 key things here. And to help us get through this talk, we just need to make sure everyone's on the same page when I mention these terms. So we've got 3 people there. And when I talk about one person, I'm talking about an observation. Right, so an individual we measure or categorize data about. And for this particular observation, we can get a value, so a singular piece. So maybe I'm just measuring the color, the hair color, for example. So something I categorize information about that observation. And when I do this for all observations, we call this a variable. So a measurement of the same kind of information here. And these variables can be numeric, so data that's best described with numbers. So typically measuring height, blood pressure, you name it, anything that can be, we don't need to write out a sentence to say what it is. Or categorical data that can be best described with text. So such as my hair color is black, Nancy's more of a brown, and so on. And you may find that sometimes with categorical data, you may incorporate numbers into it as well, and that's because some value of that measurement has to be represented with text. So that is what we're working with, and what we typically teach in introductory stats a variety of different straightforward visualizations to try capture components of our variables that we measure from our observations. So say, for example, we've got one numeric variable. We may consider what we call a dot plot, where we just visualize the location roughly about where each value is of our data set of observations. And we can see here some values are more frequent than others. And you can kind of imagine this dot plot, once we start getting too precise, so increasing the numeric precision of our measurement, the dot plot can, in a sense, fall apart. And this arises to our famous box plot. And one thing you may notice right away is that we've kind of hidden away pieces of the data, right? And the box plot's essentially visualizing not the data itself, but some numeric measurements, such as what's the lowest value, the highest value, the most central value, so what's the middle of your data, as well as the central 50% of the data, where that lies. So that's that box component there. And we can, improve on the dot plot with a histogram, which allows us to deal with numeric measurements with high precision, or a density plot. So these are different ways of visualizing a single numeric variable, and we can kind of see that they're all kept, particularly the dot plot, histogram, and density plot. We also get an idea about frequency, so how common a value is, and the box plot, it's too busy, that's probably our best bet. Now with one categorical variable, and remember this is a statistician giving a talk, we don't have as much variety compared to numeric variables. It's just bar plots and more bar plots. So the key thing here is that for bar charts, we're typically visualizing the distinct values of a categorical variable and then effectively counting how many of them we see. So here, for example, visualizing the number of penguins we have for each species, and we can represent this as a count or as a proportion out of the total sample size. So how many observations we have. And we can all kind of see that for one categorical variable, the proportion and the count gives us the same information. Now we build upon this for, say, two numeric variables. What we tend to do is scatter plots, and I don't think I've ever seen anything more than a scatter plot for two numeric variables. And that's because they tend to be quite intuitive. So we take two variables about our observations, and we use one variable to determine where it lies on the vertical axis, so the y-axis here, and the other with the x-axis. And true to the word of the Locke et al. Point I mentioned earlier, we get a very quick idea of what's going on with this data set. And you would kind of intuitively think that, as bill length increases, bill depth increases, because these penguins, a bigger penguin is, the bigger its bill should be. And we can kind of see that clearly here. But I find if you just use a correlation coefficient, you might not get that piece of information. And that's because there's actually, as you saw in the previous slide, 3 different types of penguins in this data set. Now for two categorical variables, however, things get a little bit tricky. And that's usually because we're trying to compare across different levels of a categorical variable. So maybe we're looking within Ireland, what's the species distribution? And we typically tend to embed one piece of additional information, no matter which way around you want to do it. That is the sample size, because for proportion, everything's relative to each other. And if we were to plot the raw counts, you start warping the plot very quickly. So by using the sample size within each island, in the width of the bar chart, we get an idea that, yes, all the penguins on Torgerson Island are Adelaide penguins, but there's actually fewer of them compared to the two other islands. And that stacked categorical, the stacked bar chart we saw earlier, we can use it as well. And here, another way you can try to communicate how many observations were used to calculate each proportion can be represented via text. And we get it quite quickly that, yes, Torkelson has the fewest amount of penguins, but all of them are Adelie penguins. And then for Dream and Bisco, they are Chinstrap, Gentoo, or Adelie penguins. And one thing you would note as well, for particularly with categorical variables, do leverage reorganizing the location of those bar plots, such as easy to read. Now, you're probably thinking, what about one numeric and one categorical variable? How would you visualize that? Well, we've got some of our basic building blocks from one numeric variable as well as one categorical variable. We can try and leverage that here. So here I've got a side-by-side box plot of bill length by penguin species. So I'm using a box plot here to visualize what that distribution is in terms of descriptive statistics, and then using the size of the box to communicate the sample size. I bet it's not as great as I would like. And we could also maybe just try stacking density plots on top of each other. Which plot you end up going with, that does depend on your research question. For example, if I was interested in classifying penguin species based off their bill lengths, I might prefer this right-hand plot a bit better, because you can kind of see, most of the Adelie penguins tend to have less than 4. Their bill lengths tend to be much shorter than the rest, right? But you will start iterating on these visualizations to get a better understanding of your data. Which does bring us to the core part of the talk, which is effective data visualization and some principles for it. And the first one does come with data management. And you recall how I talked about observations, values, and variables? Well, if you prepare your data in a way where your observations are, say, rows of your Excel spreadsheet and your variables are columns, no matter which plotting software you use, maybe except for Excel, because Excel is weird, you can generate any kind of plot that you want, or reorganize the data to get the plot that you want. And tidy data is the most convenient kind of way of thinking to do that. Because once you start working with metadata with data visualization, especially if you're coding it, it gets really tedious. On that note, the second principle for data visualization is be willing to iterate on your visualization. And this is especially the case when you're developing a figure for a presentation or for a manuscript. Because whoever's looking at the plot is going to see a pattern straight away. And you want to make sure that you present it as clean as you can. So you can see here in this illustration, the best way you can do it is try presenting it with a story. But to get there, you need to organize your data first, and you need to present it nicely in order to demonstrate that pattern. Third principle, if possible, stop hiding your data. This is very easy to do with box plots, because we are just visualizing 5 descriptive statistics effectively. And if I show you the actual distribution of these data, here, we can see that the box plot doesn't actually communicate very nicely for this data, that it's actually got 2 peaks. So your choice of data visualization is going to depend on what data you have. So for example, if I see a box plot, I'm probably expecting as a statistician that we've only got at most 1 peak in our data set. And if that's not the case, the box plot's not really a great visualization. And on that note, you can tweak this histogram to have 1 peak as well. It's very easy. So do make sure when you aesthetically design your plots that you don't hide too much. Point 4. Deceptive perspectives are a big deal in statistical data visualization. So for example, it's very common for people to include the zero axis, and for the most part, that is a good practice. But do consider the context of your data and what story you're trying to tell with it. Because if I present this plot on banana production worldwide, it doesn't look like it's growing that much, right? It's like going from about above 100, tending towards 150. But if I presented it with the plot on the right, I can tell the person presenting it can very easily tell a much more exaggerated story. And even though this saves the most white space, someone reading the plot initially may think that there's a sudden increase going on. So do be aware that perspective of the data visualization does matter. Point 5, use components your target audience are familiar with. And the famous word of Sir Topham Hatt from Thomas the Tank Engine series, this can cause confusion and delay for your audience in interpreting your plot. Now, for this plot here, I think depending on which field you come from, the bar chart's actually representing a mean. It's not a frequency. And even then, those little error bars up there, so these little T's, depending on which field you come from, that could be anything. Could be a standard deviation, a standard error, confidence interval. And you recall from Liz's talk, a confidence interval goes both ways. So do use components in your data visualization your audience familiar with. Even if I iterate on this plot to be a little bit clearer, we still have the issue that we are visualizing a mean, I think, because we don't have like a dot plot going alongside of it. But what are these ribbons here? Are they standard deviations, errors, confidence intervals? And even with the final iteration here, where we actually visualize the actual data points, you still need to talk to the plot to get someone to interpret it correctly. So one additional piece of advice here is, if you think someone's going to misread your plot, try find some way around it, either by including some annotation in the plot of what components represent. Number 6, this is more of a thing when you get more artsy with your data visualization while trying to visualize data. Is there anything people have noticed what's wrong with this plot just within the first 10 or so seconds as I'm speaking to it? Yeah.
75 to 82% is not at all represented by the books.
Yes. Right, and this leads back into the deceptive perspective part, but it's quite distracting, a lot of these books as well. There's another piece here I'll talk about why I don't like this plot, but you can see here we can easily distort it when we try to include more graphical components in our plots. So here you can kind of see that whoever generated this infographic had their story to tell, and they exaggerated differences. So the more graphical elements you introduce into your plots, the more junky it is, and that could be quite distracting or deceptive. So do avoid it. There are cases where including nice graphics is great in plots. We might see an example of that, but for most cases, it's not, and that's because the human eye is really good at picking up patterns, so we can tell the wrong story very quickly. The 7th one, so I'm not colorblind, so I can distinguish between the first pie chart and the third pie chart. But for some of our colorblind colleagues and peers in this room, you can't distinguish between the first and second, which is looking at heat map colors, and then with the default color wheel in the fourth, we can see that red and green look quite similar in that fourth one there. Color choice is very important because we can draw out emotion, we can try make things a lot clearer to whoever's reading our plot. Do keep in mind, the more colors you include, the less colorblind friendly your plot's going to be. So choose your colors wisely and choose your colors carefully if that is of concern. And this is probably more so for presentations rather than for manuscripts as well, for generating your plots. And last but not least, three-dimensional plots are typically a trap. There are virtually a lot of studies, or I say a lot of studies I've been exposed to when learning as a statistician, doing undergrad stats, where 3D plots are very deceptive in the sense that you can't easily compare between quantities in 3 dimensions. And for the most part, you can see here in this cartoon, those who need 3D plots are the people talking about how bad they are in terms of data visualization. That said, these principles can be held, they can be bent and broken. So how can we see good applications of these principles and how can we bend them? So the first one, I would like to revisit the iteration point here. So even though my figure caption gives it away, if we have a look at this first scatter plot, I can probably tell you right now that most people would not guess there's 1,000 observations plus in this scatter plot. And ways you can iterate on this, so these are 2 straightforward ideas. You can introduce transparency and maybe using a solid colored dot to try communicate where most points are more dense. You can see here on a projector, this looks horrible. On my computer screen, this looks great. So do keep in mind that how you try to represent density of how many points are in a particular point does matter on your presentation medium. And in fact, 2D binning, so in this case here, what I do is draw a hexagon on top of the scatter plot and then count how many points there are within that hexagon. See here on the projector screen, that communicates that most of our data points are within that centroid region over here. And there's fewer points as we go out. Maybe we could iterate on the choice of color as well to make that more obvious. But you can see here, the key thing I want to communicate is that iterate your plot on where people will see it in. Because different choices may work for some mediums, but not so much for others, as we can see here with the choice of transparency projected on the screen. Example 2. So typically when we plot two numeric variables, we don't add in more data. And that is a strong and hard rule for most statistical data visualizations. But what happens if you've got a set of data that's correlated with what you're trying to visualize? So here I've got the COVID-19 data in New Zealand from 2023 up until 2026. And here with enough artsy finagling of the scales of our y-axis, we can actually see quite clearly that the spikes in the wastewater, which is the green line on this plot, tend to align with the spikes in the case reports, which is the line in blue. And this is probably one of the best examples of when you can get away with 2 y-axes. Generally speaking, plotting multiple sets of data on the same plotting region, my advice here, if you want to bend that rule, make sure that they're at least in a sense correlated. Otherwise, it will just look very out of place. And the reason why I like this example is because it's a really funny URL called poops.nz. The third example I've got here is on more so the use of color and flipping the standard histogram upside down. So this is more of an infographic that uses data. And if we were to flip it the right way around, we can see that it's just a standard histogram. What this particular person has done here is that they made it a bit more emotive. So if you recall the second point I started for talking about why we visualize data. They're trying to present a story. They use the color red. They added quite a few annotations to highlight certain events of the war in Iraq. And we can still see that we are still getting the same information, right? We can see the death toll is a bit higher to start, goes, drops significantly, and then gets quite bad in the middle, and then tapers off. And this is more when you can start getting more artsy with your data visualization. You can use this to evoke emotion by just changing the color. So keep that in mind as well when you're presenting plots of your data or statistics. Color choice does invoke emotion. My fourth one here is a very interesting variant of a scatter plot. And chart magic in the sense that they've carefully chosen how to communicate extra information about each point. So on the bottom here, we've got the points on the bottom which don't have any flowers or poppies. Represents when a war started. And then each stem is connected to a poppy, the top here, which represents how long a war lasted. And that's kind of artistically linked with a curvy line. So we get from this plot an idea of how long wars last for, from 1900s to 2010. And the size of each of those points is communicating how many deaths were recorded in thousands. So we can kind of see the impact of each war. And then the choice of color here is just representing which region the war was done in. So we can see here that it is really pretty, and it's still clearly communicating what we want to show, how long wars last, and the death toll of each of those wars, and where they're taking place. So it is very possible to get a clean data visualization that's emotive while using really simple changes, such as changing the shape of the point, as well as color. My fifth example here, I'll let you digest that for a bit. This is a statistician's most hated chart. This is along the same hatred for 3D bar plots, because people struggle comparing the size of triangles with each other. And the same goes for the pie chart's close cousin, I guess, the donut plot as well. And what's one thing you notice that's really, in a sense, infuriating about these plot annotations? So I think everyone here is going to agree each pizza slice is about a sixth of the pie chart, right? But our plot annotations are 42%, 60%, 56%, 33%, and so on. So this builds upon that principle that if you're going to make use of a plot, make sure it aligns with how people read it. And if you're including these kind of annotations here, make sure those annotations actually align with how people visually perceive the plot in the first place. So realistically speaking, they probably should have presented a bar chart, but I suspect for these data, people tend to have pineapple with ham, right? So do think carefully, how would you iterate on this plot? I mean, excluding the fact that it's a pie chart, maybe figuring out some way to visually show those annotations first, might be your first good step. So, talking about three-dimensional plots, do remember you always talk to your plots. So here, this is a plot I gave at a conference where we're looking at probabilities. So that's the top row. And the issue is that in my context, we tend to show probability over space and to show probability of detecting an animal. So my kind of point here about 3D plots is that you need to think very carefully, A, how fast will your audience get it when you describe it with, say, 10 seconds of their attention span? And B, make sure that it makes sense to your audience in some other way as well. Maybe it just may include a slide before it to describe what's actually going on, or showcasing some math here. As in this case, what's really nice for this 3D perspective is that I'm showcasing how probability changes over space. So we can see that for some of these different shaped probability functions, we get different shapes showing in 3 dimensions. So that said, 3-dimensional plots are very hard, and because you're not an ecology audience, right? So talking to the audience that you know, this has probably caused confusion and delay. Right, so if you are going with 3D plots, try and make it not deceptive, but also make sure that your audience is going to get it within, say, 10 seconds. Otherwise, rather than listening to me, you're trying to figure out what's going on with this plot. And our last example is talking about statistically significant results at the 5% level. And this is a question I was asked about the first time I gave this talk. And I had quite a lot of thought about this. And the main reason why this topic does come up is because one of the most well-known software for producing plots, Prism, GraphPad, does plots like this, where they may present mean, presented as a point, and then we put their confidence intervals about those points as error bars, and they do a brace between two groups if it's statistically significant at the 5% level, and some quotation about what the p-value is. Now, we can see that the p-value is smaller than 5%, but for the keen eye, you may notice that our confidence intervals overlap. And for those of you who are not, let me phrase this a bit better. So for those of you who are not in the know, this can happen with overlapping confidence intervals. But for someone who doesn't have a lot of stats training, they will be asking if this result's wrong because the p-value is less than 5%. So my advice here, if you really want to bend the rule to visualize statistical significance, try visualizing the statistic on the scale that it was calculated. So for example, if I want to say that these two groups are different, the more appropriate visualization to do is to plot the mean difference between the two groups and the confidence interval for the mean difference, and then instead make use of the fact that null value for that hypothesis test is most likely to be 0. So the reason why I say most likely to be 0, if you've worked with engineering applications before, 0 is not an interesting null value. So do make sure you demonstrate that, and that will get an easier workaround than trying to explain to someone that this is a valid result, that the groups are different even though the confidence intervals overlap. So that brings us to an end of this talk. Thanks for listening. Hopefully you got some ideas about how statisticians think about data visualization, and then some ideas of how you can bend those principles I talked about today. Thank you.